Hello my dear students, I hope you are enjoying this series on vector calculus. What we are doing in last few videos, that is called differential geometry actually. So somebody wrote a comment that it is differential geometry, that you are right, it is differential geometry. But since we are studying the subject of vector calculus, so I didn't mention it like specifically, but yes, you are right, it is differential geometry. So basically differential geometry is basically you have curves in three-dimensional space, and then you are doing the analysis of these curves. That is differential geometry, and that is what we are doing in these videos also, but with the help of vector calculus. Okay, so in this video we are going to define a very important thing, which is a moving frame, right? So what it is, so you have a curve, right? So you have a curve at a point, we know that, and how the curve is defined, there is a parameterization of the curve, right? So from t belongs to an interval I, we get x of t, right? And we have a curve at every point, and we had this condition that if x prime t is non-zero, okay, at every point, then we have a unit tangent vector, which is x prime t divided by modulus of x prime t. This is what we have seen already, right? So this condition will be there for sure whenever you are defining a moving frame. What is a moving frame? What is a frame? Frame is basically a set of three mutually perpendicular axes, right? And where we can study our motion, right? So most of the time, like when you were doing using Cartesian geometry or three-dimensional geometry, so you had fixed x-axis, y-axis and z-axis. That is true, that we can always work with that. But in case of when you have space curves, we also have a moving frame, in the sense that at every point we have a set of three perpendicular vectors, right, which are like these three vectors are moving along with the points. That's why it's called a moving frame. So that makes sense. So the first condition for a curve to have a moving frame is the first condition, this one, that x prime t should not be 0 at any point. There is one more condition which I'll tell you. Okay, so let me write down the conditions first. For a curve, for a space curve xt to have a moving frame, so the conditions are, first condition is x prime t should be non-zero, and the second condition is x prime t, x double prime t, the multiplication should be non-zero. Okay, so this is the condition. So this tells you, the first condition tells you that the curve never has zero speed, okay, and this tells you that because this is already non-zero, so x double prime is 0, so this tells you that when is x double prime 0 for a curve, if curve is a straight line. So curve is not a straight line, so if you have a straight line, you don't have a moving frame, right? So these are the two conditions. This we know that we'll see that where we are going to use it, right? So now my next thing is that I want to define the moving frame. That means I want to define three perpendicular vectors, right? Okay, so and I also want them to be unit vectors. So the first vector would be, we already know, we defined unit tangent vector. First vector of the moving frame, is unit tangent vector, which is defined as x prime t divided by modulus of x prime t. So this is our first vector in the moving frame, and here you see I am using the first condition. Note that condition 1 is required, otherwise your unit tangent vector is not defined. Okay, fine. And in I think 2 videos before this video, we had seen that, note that we already proved the result, that t and dt by dt are perpendicular, orthogonal, right? So this we proved in the video named titled properties of unit tangent vector. Properties of, you have to refer this video, properties of unit tangent vector. Okay, fine. So now we know that this vector is perpendicular to this vector. So this should be our second candidate. Therefore, second vector of the moving frame is, I call it n vector, which is called principal normal vector. This is called principal normal vector, is defined as dt by dt divided by modulus of dt by dt. Okay. Now, if you look at the modulus of dt by dt, so you have x prime t upon x prime t modulus is your t, and you find out dt by dt, that would be, you have to use the quotient rule here, x prime t square modulus square x prime t modulus as such x double prime t minus x prime t as such derivative of x double prime t modulus. So this is non-zero if second condition is true. What was the second condition? Second condition was that x prime t and x double prime t should be non-zero. So we have non-zero terms here. So you see that we also need a second condition. So this is how we define our principal normal vector. That is our second candidate for the moving frame. And we also have a result here, little result. Note that I just told you that n is equal to dt by dt divided by dt by dt. Now, if I write it like this, dt by dt divided by ds by dt, okay, and then multiply by ds by dt and this dt by dt modulus. Now, if you look at this quantity, what is this? This is 1 by kappa, right? This is 1 by kappa, where kappa is your curvature. So this was the definition of curvature, right? If you remember, kappa was dt by dt modulus divided by ds by dt. So we get n equal to, and if you look at this quantity, use chain rule. So this is dt by dt and then into dt by ds. So this becomes dt by ds into 1 by kappa. So we have this result that dt by ds equal to kappa times n vector. Okay, so this is also a relation between unit tangent vector and principal normal vector, right? Here you have to note one thing. If you look at this curve, this is my curve, right? Fine. And I have this point P. At this point, this is my unit tangent vector and this is my unit normal vector, right? So a plane which is defined by these T and N is called an osculating plane, okay? It is called an osculating plane of path at P. This plane is called osculating plane of the path at P. Osculating means to kiss. So this plane is kissing your curve at point P. Okay, so it is defined by, you know that if I give you two vectors, you can define a plane. So it is defined by these two vectors. So at every point, we can define a plane which is defined by the vectors T and N, and that is called the osculating plane of the path. So you can be asked to find out the osculating plane. So if I give you two vectors, how can you find the osculating plane? You have to see that, right? We'll do that. Okay. Now, what else? Now we need our third candidate for the moving plane. Third candidate for the moving plane. So can you tell me who should be our third candidate for the moving plane? I gave you two vectors T and N, which are both units and perpendicular. What about T cross N? The cross product of vectors T and N, call it as B vector. This B vector is called binormal vector. This is called binormal vector. So this vector is going to be, if I look here, so this vector is going to be perpendicular to both t and n vector, right? Okay, so this, if you look at this vector, is b orthogonal to t and n? Yes, answer is yes, because that is how we are defining cross product of two vectors is perpendicular to both the vectors. And then what is b a unit vector? So if I want to check if b is a unit vector or not, so I'll take modulus of b, that would be equal to modulus of t into modulus of n into sine of the angle between them. So that is, now t is a unit vector, 1, n is a unit vector, 1, sine pi by 2 is 1. Note that t and n are perpendicular, so angle between them is pi by 2, so 1. So that means b is also a unit vector and orthogonal to both t and n. Therefore, I get this t and b is a moving frame, right? And it is right-handed. Right-handed means if I do like this is my t, this is my n. If I take my palm here and cross like this, my thumb will point in the direction of b, right? So this is our moving plane, a moving frame. Okay, so we'll see that this is very important when we are studying space curves. So to end this video, I'll just look at one problem. So we have our favorite helix, which we are using again and again in this course. This is my helix. Xt is equal to a cos t, comma a sin t, comma bt. So question is, find the moving frame for this curve. Find the moving frame for this curve. So for that, we know that our tt is simple, that is x prime t divided by modulus of x prime t. So this is equal to, you have to differentiate it. So that would be minus a sin t, comma a cos t, comma b divided by the modulus, that would be minus a sin t square plus a cos t square plus b square. So that would be minus a sin t, comma a cos t, comma b divided by, this is a square plus b square. So this is my first vector of the moving frame. Now I am looking for the second vector, that is the derivative of t with respect to t divided by the modulus. So if I differentiate it with respect to t, I am going to get minus a cos t, comma minus a sin t. This is going to be 0 divided by a square plus b square. And if I take the modulus of this vector, that would be, you see, x component square, that is a square upon a square plus b square square plus b square upon, sorry, a square upon a square plus b square square. So that is going to be, this is equal to a upon a square plus b square. So a and a square plus b square cancel. So I get minus cos t minus sin t, comma 0. So this is my n vector. This is my n vector. Okay, so now I can define my b vector, which is t cross n. So I know how to take cross product of two vectors t and n. So you can use this determinant. You write I, j, k. Then you write components of t vector, which are a minus a sin t upon a square plus b square. Then the second term is a cos t upon square root of a square plus b square. And the third term is b upon square root of a square plus b square. And here you have minus cos t minus sin t, and then you have a 0. Now we can do for I component, I'll have this and this cut. So I have this and this. So that will give me minus b. This, when I go like this, there will be negative sign more. So b sin t upon a square plus b square, right? B sin t I cap. And then for the next j cap, let me change the color. Okay, so for j cap, I have to put a negative sign here, minus j cap. So this and this will be cancelled. So I have to do this and this. So that would be b cos t upon a square plus b square. And for k cap, right? So for k cap, I will have this and this cancelled plus k cap. I have to do this and this. So that will give me a sine square t plus cos square t divided by a square plus b square. Okay, so that gives us b sine t I cap minus b cos t j cap plus a k cap divided by a square plus b square. So this is my b vector. So you understand? So you have these three vectors, this b vector and this t vector here and this, sorry, this is n vector, not t vector, n vector here and this t vector. So they are going to, as your helix is moving, right, at any point, this frame is moving along the helix, right? So what is the usefulness of this frame? We'll be doing it in the next coming videos. Please share this video, subscribe to this channel and keep supporting. Happy learning.